Very well, let's determine the values of rate constants. And we're going to first look at some simple cases. We're going to look at cases where we only have one reactant and only one kind of reactant. And we're going to concentrate on the idea of whether this reactant behaves and reacts in one manner or maybe two other different manners, which we call the orders of the reaction. So let's get right to it. All right, so as I implied before, the activation energy is ultimately what dictates how fast or slow the reaction takes place. And the activation energy itself is derived from the rate constants at any given temperature, right? And you have different rate constants for different temperatures. Now the rate itself, the rate at which this reaction proceeds forward, has an equation which very much derived from calculus itself. Simply put, the rate at which A disappears, or you could even look at it from the point of view of the product B, the rate at which the product B appears is given by the equation right here. Okay, so the rate, also known as the rate law, is equal to the negative of the rate constant if you're looking at it from the point of view of the reactant. Otherwise, this will be positive if you look at it from the point of view of the product. But the rate of the reaction is equal to negative K times the concentration of the reactant raised to some power. If the power equals 0, this is what we call a zeroth order reaction, in which case A completely vanishes because any number that is raised to 0 equals 1 automatically, right? So if n is 0, the rate will only equal negative K. But you could also have orders which equal 1 or 2, in which case you're dealing with a first order or second order reaction. Now these are rates, and this is very much a calculus thing, so we're going to see how exactly this gets affected in terms of the overall equations we're going to be dealing with. Alright, now if you have a reaction, a balanced reaction, right, where you have multiple reactants and multiple products, sometimes you kind of have to equilibrate and calibrate your own balance reaction, because the coefficients may be different for all of the things. In fact, for this example, all of the balancing coefficients are different. We have a coefficient of 1 for A, 2 for B, 3 for C, and 4 for D. So you're producing different amounts of products as you are removing different amounts of reactants, and pretty much any other combination is also different. So what we do is simply divide each one of the rates, the rate of A or the rate of B or the rate of C or the rate of D, by its own balancing coefficient to basically calibrate everything to the same base value. And that's given by the equation right here, where VI represents the balancing coefficient in front of A, B, C, and D, and then the rate of I represents the rate of A, B, C, or D. So what this is telling you is that, in essence, for this balanced reaction, if you want to equilibrate and kind of keep it consistent, the rate of A will be divided by 1, the rate of B will be divided by 2, the rate of C will be divided by 3, and the rate of D will be divided by 4 to make them all equal to each other. The other thing too is that the reactants, they will always have this negative in front of them, but the products will have a positive value, because when we're talking about rate, we're either talking about the rate of disappearance, meaning that you have less and less as time goes by, and so final minus initial ends up yielding a negative value. So this negative in front kind of like gets rid of the negative altogether. It's almost as if you were taking the absolute value of it. But for the products, you produce more and more products, so final minus initial amounts end up being positive, right? And so this is why all of these things equal each other. All right, now the other thing too is that with these relationships, you could actually say, well, if you know the rate of A, you could use the relationship right here to find out what the rate of B ends up being. And simply stated, you solve for the rate of B, you will multiply by -2. And when you do that, the negatives cancel out, and you end up basically saying that, yeah, if you multiply the rate of A by 2, that will equal the rate of B. The same thing goes for C. Multiply by 3. In this case, you have rate of A times -3 will give you the rate of C. And for D, if you multiply the rate of A by -4, you get the rate of D. So this is a nice, nifty way to actually derive each of the individual rates in respect to the corresponding reactant or corresponding product. Now, one of the techniques, and it's not the only technique, but the technique that is most often utilized in general chemistry to determine kinetics is UV spectroscopy. Specifically, the idea of absorbance. Because absorbance, as you may remember from our previous lectures, is related to the concentration of the solute. And the absorbance increases as the concentration increases. So you could, in essence, look at the absorbance of a solution and see how the absorbance is changing over time to get an idea of the rate of the reaction. But if you want to be more technical about it, technically speaking, to get the concentration of your species to find out how the concentration is changing over time, you have to take the value of the absorbance and you have to divide it by the absorptivity constant and the path length. All right, we're going to now dwell into the simple case, the zeroth order simple case. As I told you already, a zeroth order reaction implies that the exponent of the rate law, negative Ka to the n, gives you an exponent of 0, which basically cancels out A altogether. And this tells you that the rate in a zeroth order reaction is simply a constant, is negative K. It's the rate of the reactant disappearing is going to remain constant as time goes by. It's not going to change with its concentration. All right, but as I told you earlier on, this is in essence a calculus term, and rates in calculus can be given and restated as the change, which is represented by the lowercase d, the change in the concentration of A over the change in time. So you're basically looking at molarity per second or molarity per minute or molarity per hour, whatever the actual time frame may be. But if this is a zeroth order reaction, that rate will have to equal only negative K. Okay, now here I'm going to tell you that I don't expect you to know or understand calculus to pass this class, but I want to show you this because it's a simple derivation, and for those of you who have had calculus, this will make the whole process a lot simpler. For those of you who haven't taken calculus, you can basically ignore what I'm about to show you in terms of the derivation, but you will still be on the hook for knowing how to utilize the final equation that we want to derive from this. But when it comes down to calculus, there's something known as separation of variables, which technically is the same thing as saying that dA over dt is nothing more than a division. And as such, you could basically cross multiply the term on the denominator on both sides to end up with dA equals negative k dt, dA being the change in concentration of A and dt being the change in time. All right, now here's where the calculus actually takes place. When you have changes of something and changes of something else, you could do what we call an integral. You could take an integral of both sides. And specifically, you could look at the change happening from the initial concentration, A naught of the substance, to some final concentration at some given time. And here on the right side of the equation, you will go from time 0 all the way to whatever the time may happen to be, right? So we just call that t. And when you apply calculus to this, what you end up finding out is that on the left side of the equation, you're going to get final concentration minus initial concentration, which is the change in the concentration. And over here, you'll have final time minus initial time, which is basically 0. So this will end up being negative k times t, all right? And so now we have a pretty simple equation that correlates the final concentration, right? So if we solve for the final concentration, we end up with a new equation right here, an equation that tells you that the concentration of A changes over time, and it depends on what the initial value is, right? But more importantly, what this is basically showing you is that if the reaction is truly a zeroth order reaction, if you were to make a plot of the concentration of A versus time, you ought to get a line with a negative slope. If the reaction is not zero order and you plot concentration versus time, you should not be getting a linear plot. So that's kind of the dead giveaway that you may have a zeroth order reaction. And this particular equation is what we call the integrated rate law, because we have quite literally taken the integral of what used to be the rate law of the equation. Okay, so this is something we're going to use in the following examples. All right, now just to give you a hint of how we tend to do these things, usually the way this works out is that you have a table of concentration versus time, which is kind of what you would end up getting experimentally anyway, because what you will be doing in the lab is take a solution, mix the reactants, place it in the UV spectrometer, and start collecting absorbance data. And so you would actually collect different absorbances at different time. And knowing the value of epsilon will allow you to basically change the absorbance to concentration. So you end up getting all of this by doing the experiment. Then comes the data analysis. And what you basically have to do first is make a plot of concentration versus time. If the plot of concentration versus time gives you a straight line, and in this case the correlation value is excellent, it's almost -1. This is basically telling you, yeah, this is a linear plot. This is definitely a zeroth order reaction. And so we can use the equation, the y equals mx plus b equation, to derive the value of the rate constant. Simply stated, the value of the slope of this line is the rate constant. So it's as simple as that. Once you plot the the value on the y-axis versus time and you get a line, the slope is automatically the value of the rate constant. And mind you, the value has to be positive, right? So don't bring that negative along for the ride. But this will be the value of the rate constant. And with the value of the rate constant, we can actually calculate the initial rate of the reaction from the point of view of A. And since this is a zeroth order reaction, we multiply -k by the concentration to the zeroth power, which is to say that the initial rate is simply -0.00154 molarity per second in this case. Actually, molarity per minute, since the time is actually in minutes. All right, so this is actually molarity per minute. But this is how you go about finding out the rate constant and utilizing the rate constant to get the rates. And once you have the rates, you could actually use that to switch over from the rate of N2O to the rate of N2 or the rate of O2 using the related rates that we discussed earlier in this video. All right, so I want to stop at this point here now that we have discussed the zeroth order reaction. And in the next video, we're going to discuss both the first order and second order reactions. So see you in the next video.